Morning, guys. Today we're going to talk about optimal control. We're going to define the problem. We're going to look at a couple of examples about why its nuances are necessary. And yeah. All right. So the basic problem is, again, given the dynamics, these are nonlinear dynamics. It could be linearized. This is just the most general form, where we have x dot is equal to f, the dynamics of our system, which is a function of our state and some input value. And so when we're talking about optimal control, we're going to be looking at the dynamics, the states, and we want to design this value u subject to some constraints, subjected to some cost function, and we want to optimize the evolution of our system with regards to those. Okay, so given this general system, suppose now that the function f depends on some control u, right? So we want this to be equal to some value a with parameters included in some set. A, which is a subset of Rm. All right, so the function will be a mapping the function f is a mapping from Rn cross A to Rn. All right. So this notation, if you haven't seen it before, this just means that the function f is a mapping from Rn, so from this space, from these argument inputs, and this is the argument output. Okay. So from this to this. Great. All right, so then if we select a value A, which is in the set A, and consider the corresponding my notes over here. All right. And consider the corresponding dynamics as follows. We get x of t is equal to f of x and a with initial conditions at x naught. This should be a t. All right, so I'd note that a is just a scalar value here. Then we can use various methods to determine the evolution of x when a is constant. Okay. So maybe we don't want a to be constant. Maybe we want a to move, or we want to define a as the function u. We want to define the input as maybe being many different values as time evolves or time moves forward. So the next possibility is that we can define a function alpha, which is defined on time, and then this maps to the set A. Okay, so we can define alpha as maybe being, make this bigger, great. Alpha of t is equal to as being maybe a piecewise function where it's equal to a1 between 0 and between t equals 0 to t equals 1, equal to a2 between the values of t1 and t2, and equal to a3 for the values of t2 to t3, and so on. Okay, so this gives you an idea of how this should be equals there, of a potential function that we can use. So this is for there we go. 4 times 0 is greater than t1 is greater than t2, and a1, a2, and a3 all contained in that control space. Okay, so then we get the dynamics equation. The dynamic equation x dot is equal to f of x and alpha, right? Makes sense. At the initial condition equal to x naught. Okay, and note, I think I'll keep moving over, okay. And note that the system may evolve or behave differently as we change the control parameters. So for instance, how much space do I have? Yeah, great. Okay, so for instance, if we plot time on this trajectory or on this axis and x on this axis, it's not going. There we go. And x, and then we have, so we have t1, so this is t naught, then we have t1, t2, and t3, and we started with initial condition x naught. So now in between each of these regimes, we're using a different control actuation, right? So during this control actuation, we're going to be using basically u is equal to a1. This will be u is equal to a2, u is equal to a3, and so on. All right, where u again is the input into our initial function. and then alpha is different values of different A's, A1, A2, A3, at different in between different intervals of time. Great. So we started the initial condition. Between these two times, we could flow maybe this direction, and then between A2, between T1 and T2, A2 is taking control, and we could flow down this way. A3 flow back up, and so on. But it could, depending on the input and the input's effect on our system, it can dramatically affect how we evolve. So we can call alpha a control. But note that it's an open loop control, right? We're not using our state to feedback our system. We're just applying an input and expecting our system to behave as we intended to. All right, so now I mentioned that with optimal control, we want to optimize relative to something. So here we call this the payoffs or cost. Okay, so our overall task will be to determine what is the quote-unquote best control for our system. Okay, and so to do this, we need to specify payoff criterion, which we call or payoff function. All right, so we're going to call this as P of alpha T, or of alpha, yeah. All right, which we're going to call is equal to phi of x at capital T plus the integral between 0 and capital T of this function L of x and alpha of T, dt. Okay, maybe I can move this over a little bit. There we go. All right. All right, and for this system, we have that where x is, where x solves for the control, alpha. Okay, and L is a function in reals to A, just to the Rn to cross A to reals, and phi is in Rn mapped to R. L is called the running cost. Or actually they say running payoff here. But you can also in the literature find it as, I think it's the cost to go. A fee is the terminal payoff or terminal cost. All right, and we also for this particular payoff, we also need to specify the final time. So t is the final time. And so these three things are needed or given. So by that I mean we either need to design what they need to be for our system, or they need to be given to us as the design requirements. All right, so now the basic problem. All right, so what is the problem of optimal control? So it is to find a control alpha star which maximizes payoff. So in other words, we want P of alpha star to be greater than the payoff of alpha for any other value for all other controls of inputs to alpha. So for all alpha in A. So this says that this expression right here says that we want the payoff of the optimal solution of our system, the optimal control, to be larger than the optimal or than the payoff for any other values of alpha. Okay. So then this is called alpha star is called optimal. All right, so now we have to take in a couple issues or potential problems when designing this. So this task presents us with these mathematical issues. All right, so the first one, existence or feasibility. Does an optimal control even exist? How can we characterize an optimal control mathematically? Three, how can we construct an optimal control? and there's more. So the first one gets into before even going through the process of designing an optimal controller, can we? The next one is, the next two are talking about actually writing down and defining an optimal control problem. And subsequently talking about its characterizations and its construction. So making sure that we're designing our optimal control problem in such a way that it's will lead to a valid solution. All right, and that's all I have for you this talk.